Hello everyone, welcome to my channel. This series is a series of tutorials on OpenMP implementation in Fortran. Now in this tutorial series we will be looking at the different commands and functionalities that are available in OpenMP through which you can make your Fortran programs work faster and in parallel mode. Okay, now in this video I'll be talking to you guys about OpenMP, the brief outline of what it is and how it works and stuff, some details about it, and what you need to get started with it. Okay, all the images I provided in this video, in this presentation, they're all available from this source, https computing.llnl.gov and tutorials. Okay, that's for the information. Okay, now let's get started with it. Now, what is OpenMP? OpenMP stands for Open Specifications for Multiprocessing. No, some people also call it as an API or an application programming interface. So what does it do is that it sits on top or works on top of a compiled programming language and makes the programs run faster. So to imagine this, it's like a booster or some kind of an added accessory to a car that makes the car run much faster. Simple as that. Simple as that. Let's see how it works. Now this technology has been applied to compiled programming languages like C, C++, and Fortran. The reason why this is applicable to them is because in compiled programming languages, before the executable is executed, all the code requirements, for in terms of memory functions is known from the beginning till the end of the program. So as a consequence, you have the entire plan ready and you can optimize it at the required places. But in an interpreted programming language, since the commands have been executed one after the other, there's no foresight on what the memory requirements that will be applied in the future, or the functional requirements that will be applied in the future. Hence, this technology is not that easily applicable to interpreted programming languages. Now, how does this work? It's simple. What it does is that it uses preprocessed directives, functions, and subroutines. Okay, in the program. These things command the compiler to do certain operations stringently. Usually, the Fortran compiler, when it's given the code, it reads through the code and decides what to do and what not to do and everything. Okay, but here these preprocessed directives and functions and subroutines, they actually command the compiler to do certain operations as per their wish. Okay, so here the compiler gets commands telling that hey, do this and do that and stuff. As a consequence, the machine code that gets generated due to their influence is little more optimized and has flexibility that makes it possible for running the code in multiple processors. So simple as that. Okay, so now the implementation is simple. What you have to do is that you just have to take a serial program, just have to take a normal Fortran code which works perfectly in a serial mode, and then add some corrections to it. Or I would say tweak it slightly using OpenMP, and that's about it. Once you do that, everything works fine. That's the advantage of OpenMP. So when you do that tweaking, you can run the code in serial mode as well as parallel mode without any disturbance. Okay, and during this tweaking process, the user should specify the appropriate preprocessed directives, functions, and subroutines in the regions where parallelization is possible. Okay, that will know as we go along as to which region is parallelizable and which is not. And this works on a shared memory system. This technology is built for shared memory system. Okay, so let's see what shared memory system is. A shared memory system is something similar to this. It's a condition wherein the memory is located in the same hardware, and all the processors have the capacity to access each and every bit of the memory directly and easily. For instance, your laptop, your simple desktop, your mobile phones, your tablet, all of them come under shared memory because the processors in them they have the RAM memory in the same motherboard as the same motherboard, and as a consequence, they all have access to the same memory without any disturbance. So, okay, they all share the same memory. If there are multiple processors, they all share the same memory. So that's the reason why it's called a shared memory system. So that's about it. And now let's look at the syntax for the preprocessor directives and the commands. Now the preprocessor directive, okay, it's pretty simple. What you have to do, you just have to write a Fortran code. You just have to write a Fortran code like this. Sorry, just have to write a Fortran code like this. Just put the exclamation $sign in the front, and that's it. That becomes a preprocessor directive. For instance, this command over here, print hello world from OpenMP get thread num. Okay, this line is actually a normal command. Okay, just by putting an exclamation $sign in the front, it becomes a preprocessor directive. Now the advantage of this is that when you run this command in a serial mode, okay, because of this exclamation sign in the front, this line will be taken as a comment and it will be ignored. On the other hand, when you run this in parallel mode, this command will be taken into consideration. Okay, so and this function will work, this command will work in parallel mode. Simple as that. So remember, if you put something with an exclamation $sign during serial execution, this will be avoided. In parallel execution, this will be taken into consideration. That's about preprocessor directives. Next, what you have is that blocks are constructs, so they are also called as normal directives. The syntax for them is simple. You write exclamation $sign followed by OMP, and there should be no space between dollar and the OMP. Okay, and then you write the construct name or the class name or the block name, and then followed by the arguments that the class or the construct might take, and then what you do, write the program code in between, the Fortran code in between, and end the block using the same command or exclamation $OMP, and end is sufficient. But for the sake of good program practice, write the construct name or the class name to finish it. Okay, that's a simple syntax, and that's about it. The syntax is not that difficult as one might anticipate. Next, with that being said, what do you need to start with? All you need is just a normal Fortran compiler. I'm using GNU Fortran, and if you guys have some other version of Fortran like Intel or Intel or NAG or PGI, it doesn't matter. All you need is a Fortran compiler, preferably latest version, because that latest version will have the latest versions of OpenMP commands in them, OpenMP definitions in them. That's it. All these compilers have predefined OpenMP commands and subroutines, etc. built into them. So if you install that, that's more than sufficient. You don't need anything extra, and you can get started immediately. And the OpenMP would not be complete without mentioning a little bit about MPI. Though in this tutorial we'll not be seeing about MPI, so it's better you guys know a little bit about it, so that you guys have an understanding what it is. MPI stands for Message Passing Interface, and this works on a distributed memory system. Now, what a distributed memory system is something like that looks like this. This is a distributed memory system. Here, the memory is actually the entire memory is not as a single entity. Rather, it's actually clustered and distributed in different machines. Okay, and all the CPUs do not have exclusive rights to the memory, to one particular memory, whereas they have exclusive rights to only a fraction of the memory. For instance, if you look at my cursor over here, these 4 CPUs have access to this memory exclusively, whereas these 4 have exclusive access to this memory, but they cannot access this one or this one. Similarly, likelihood goes for everything else. So how to imagine this? Imagine this being an independent computer or an independent processing computer machine. Okay, all of these as individual units connected by some network through which they can exchange information. Simple as that. Okay, now this is how a distributed memory system looks like, and MPI is exclusively defined for this kind of this kind of systems. So the program is defined when an MPI program is defined. It is defined such that the entire program runs on all the given processors simultaneously. and then as the program runs, selective parts of the program gets executed by different processes. It gets done by different processes. Okay, so the selective elements are done by different processes. So and what happens if some job is done by one processor, another job is done by other processor? Then ultimately, eventually, they have to come to a point where they have to one has to collect all the information from the given to these processes, right? So that's where the magic of MPA comes in. The results or the data are passed between processes using message calls and receive calls through the interfaces. Here, the messages are here. All the data that has to be given to these individual CPUs or blocks. Okay, other than the results from these data are actually sent to others or received from others, okay, by passing them as messages through the interfaces that connect them. Here this interface is nothing but your internet or your fiber optic cable connections, or any data wire connections that connect these computers. Simple as that. Okay, and that is how it works, and that's why they call it message passing interface, because the informations are passed as message calls through the interfaces. And here the downside of MPI programming is that this program is inherently parallel right from the beginning once you make it, so you cannot run this program in a serial mode. You cannot do that. It's pretty complicated to do this in a serial mode. Okay, with that being said, this is the end of this tutorial. Thank you guys for watching, and now in the next tutorial we'll be going with a direct example. We'll be writing a hello world program using OpenMP. Thank you guys for watching, and see you guys next time.